So in a previous video of mine, I just came up with this question. The limit of a1 to the power n plus all the way up to an to the power n raised to the power of 1 over n as n approaches infinity, where all of the terms are non-negative, motivated by a special case where we only have two terms inside the bracket, where the limit should be equal to the value of the larger term of that two terms. If we have finitely many terms in that bracket, then that limit should be equal to the maximum value of that term. Now we have actually infinitely many terms as we let n approaches infinity. So every time when it comes to infinity, things get very tricky. So to deal with this question, we need to be very careful. And we have to first divide it into two cases. First, case number one, if the sequence is bounded. Case number two, if it's unbounded. Using our well-known lemma, limit of n raised to the power of 1 over n is equal to 1 as n approaches infinity. So here's the proof. Here's the proof that I just came up with. But here's my disclaimer. First of all, I don't even know if the question is legitimate that I came up with. Because what does it mean by a1 plus all the way to, is it allowed? Or is it legitimate for me to write it like this, right? Infinitely many terms in here. So second of all, I don't know whether my proof is legitimate or not. But anyway, here's the proof. Case number one. So suppose if it's a bounded sequence, then I'm going to say, okay, since it's bounded, it has to have a supremum. So supremum means the least upper bound, right? Bounded means this sequence has many, many upper bounds, because all of them are non-negative. Therefore, it has many, many positive upper bounds. Out of the many, many, maybe infinitely many upper bounds, there is a least upper bound. That's the supremum. So let's just denote the supremum as beta. Beta equals the supremum of the set a sub n. N is from 1 all the way up to infinity. I'm going to claim that the limit actually equal to beta. Now, here's how. Here's why. First of all, I'm going to denote a1 to the power n all the way up to n to the power of 1 over n as bn, right? Just to be very convenient, because otherwise we'll have the bn is larger than or equal to, I want to replace every single term with just beta, so that because none of these terms is larger than beta, right? So that way I can enlarge this expression. Right, so that becomes quantity beta to the power of n plus beta to the power of n plus all the way up to beta to the power of n quantity raised to the power of 1 over n. How many of them? N many of them. Therefore, that is equal to n times beta to the power of n quantity raised to the power of 1 over n. That is equal to n raised to the power of 1 over n times beta. Now, using our lemma, that this quantity should approach 1, therefore this quantity should approach beta. Keeping this in mind, we now take the limit supremum. Limit supremum. N approaches infinity of bn is now less than or equal to, take the limit supremum, that is the limit. Limit is beta, like I just mentioned. So here is our first fact. Limit supremum is less than or equal to beta. Then I'm going to show limit infimum is larger than or equal to beta. Here's how. Now, knowing that there is a least upper bound for this sequence, therefore we can confidently conclude that if beta is reduced by a little bit, right? So given any epsilon larger than 0, if beta for beta minus epsilon reduced even just by a little bit, then this quantity is no longer an upper bound, because beta is already the least upper bound, right? So this is no longer an upper bound. So that means there has to be at least one term that is larger than this quantity. So there has to exist some term. Let's denote it as A sub k of epsilon, right? Because this subscript entirely depends on the value of epsilon, right? So this is a fixed term. So this is definitely larger than beta, than epsilon, because this quantity is no longer the upper bound, right? So at least one term is larger than this. Now, I'm going to this time replace, I'm going to get rid of, so first I'm going to let n that larger than k of epsilon. K of epsilon is already a fixed positive integer. I'm going to make little n large enough. Of course, I can do that. So in that case, that means the set of E, the set is from A1 all the way up to A sub k of epsilon, all the way up to an. Right? This little n is that little n. Right? So in that way, I can make sure that A sub k of epsilon is actually contained in this set, right? As long as I make little n large enough, exceeding this term already, right? In that case, I can safely claim that Bn now is larger than or equal to, after get rid of every single term except for A sub k of epsilon. Right? Because get rid of A1 to the power n, get rid of every other term. Because A sub k of epsilon is one of the terms here. After this term, we have other terms all the way up to an. Right? Only left with this term to the power of n quantity to the power of 1 over n, that is equal to A sub k of epsilon. And that is larger than beta minus epsilon already. Right? So we have Bn is larger than beta minus epsilon, as long as little n is larger than this fixed subscript. Now we can take the limit in Feynman as you expected. Limit in Feynman as n approaches infinity of Bn is still larger than or equal to beta minus epsilon. Notice limit in Feynman is already a constant. And now we let epsilon approach 0. Then we can have limit in Feynman as n approaches infinity of Bn is larger than or equal to beta. Right? So it's a common technique in analysis. First, we proven that lim sup is no larger than some constant. Then we've proven the lim inf is no less than the same constant. Therefore, we can easily conclude that, okay, lim sup is no larger than beta. Beta is no larger than lim inf. Therefore, simply we can conclude lim sup is no larger than lim inf. We also know for a fact that lim sup is no less than lim inf. Combined with lim sup is no larger than lim inf. Therefore, we conclude lim sup has to equal to lim inf. equal to the limit. There actually is a limit. Because lim sup equal to lim inf equal to beta, right? Beta. Right? Lim sup, lim inf equal to each other. Beta is squeezed in between. Therefore, those two constants are equal. Beta, beta, beta. Limit is beta. Beta. Case number 1 is now proven. Now move on to case number 2. If the sequence is unbounded, so that means, first of all of the terms are non-negative. Therefore, we can, given large enough positive constant that's larger than 0, then there has to exist some term a sub k of capital A. Notice that this subscript is a fixed constant, fixed positive integer. And also this subscript entirely depends on the value of capital A. Therefore, it's denoted like this, so that this fixed term is larger than the given large enough positive. So, again, like previous method, we will let little n large enough, larger than the k sub k of capital A, right, that we just found, right? This is also fixed. So as long as little n is large enough, then I can simply use Bn, again denoting this expression, and Bn is again larger than or equal to, after I just get rid of all the other terms, except for this term, right? Because as n is large enough, this term is definitely contained in A1, A2, A3, all the way up to AN, definitely contained in that. So I can just simply get rid of all the other terms, right? Except for this term. So A sub k of A to the power of n raised to the power of 1 over n, that is smaller, right? So that is equal to A sub k of capital A, which is larger than capital A. So what does that mean? That means we've actually found a fixed subscript, so that when little n is larger than this subscript, every single term in this sequence, after this term, infinitely many of them, right? Every single term after this term, right, is larger than A. Therefore, according to the rigorous definition, we can then conclude that the limit of Bn is really infinitely large. If we consider infinitely large also as a generalized concept of version of limit, right? We really found a, usually we use capital N, but here is a similar idea. We found a fixed subscript, so that as long as n is large enough, then every single term after this term can satisfy this inequality relation. Right? So exactly the definition of infinitely large. So in this case, since the sequence is unbounded, therefore the supremum of and supremum of this set is actually infinitely large. Okay. So that is also, in this case, sup. Also true. So both cases are true. Both cases are true. But again, I don't know if my proof or my question is legitimate or not. But let me know in the comment.